All right, the last section of the notes is about continuous random variables as opposed to discrete. Everything we've been doing so far was discrete. Discrete random variables where you can actually list the outcomes or make like a probability table. You don't always have to make a probability table, but you could have made a probability table. You can't do that for continuous. You can't list the outcomes because there's an actual infinite number of outcomes. Random variables that can take on any value within a range of values are called continuous random variable. So even if it's any value within a range, even if you're restricted by a range, that's still an idea of infinite values. Because there's infinite numbers between 2 and 3. There's 2.5 and 2.4 and 2.3, but there's 2.35 and 2.31, etc., etc. The normal model is the most famous example of a continuous random variable. We've already learned all about the normal model. Norm's our friend. We know everything there is, hopefully, to know about the normal model. We won't worry about how to calculate the means and the variances and the standard deviations, but we can still work with models for continuous random variables when we are given the parameters. So if you are told the mean and the standard deviation, then we can still work with these values. We will not learn at this point how to calculate those values. Good news, nearly everything we've said about discrete random variables is true for continuous random variables as well. So all the rules that we've been learning throughout this chapter work for continuous as well. This is a kind of a new statement too that you need to make sure that you know. And that is when two independent continuous random variables have normal models, they need to be independent, then their sum and difference are also normal. Their sum and difference are also normal. So if I'm asking you to add together two random events and you know those two random events are normal, both normal and independent, then their sum will be normal too. So I can use the normal model again. This fact will let us apply our knowledge of normal probabilities to questions about the sum or the difference. For example, the times required to pack stereos can be described by a normal model with a mean of 9 and a standard deviation of 1.5. The times for the boxing stage, so we have packing times and boxing times, can also be modeled by a normal model with a mean of 6 minutes and a standard deviation of 1. So I guess packing it is like getting it into that styrofoam and all that, and then boxing it, I guess, is getting it into the box. I'm not 100% sure about what's going on there. Determine the model for packing two consecutive systems. So they're only talking about packing now. Two consecutive systems. So the first thing we're going to have to do is we're going to have to assume packing times are independent. That's number one. We're going to have to assume, and let's just kind of think about it. We'll assume that the time it takes you to pack one does not influence the time it takes you to pack another one. I can kind of sit here and think about ways that might violate that, but for now we're going to just go ahead and assuming packing times are independent. When they say determine the model, well, if we believe packing times are independent, then their sums, adding two systems together, the sum would also be normal, with some mean and some standard deviation. I can find these numbers, is basically what I'm doing, is packing two consecutive systems. So the mean, we remember from previous problems, is just 9 plus 9. Time to pack one plus time to pack another one, or 18. The standard deviation, however, is not simply 1.5 plus 1.5, but is rather our Pythagorean theorem of statistics, and it is 1.5 squared plus 1.5 squared, or 2.12. So we believe, assuming independence, that packing two consecutive systems will follow a normal model with a mean of 18 and a standard deviation of 212. Now, next question. What is the probability that packing two consecutive systems takes over 20 minutes? So now you have to use your knowledge from this problem to do this next problem. We just discovered that packing two systems should take, on average, 18 minutes with a standard deviation of 2 minutes and 12 or 2.12 minutes and follow the normal model. So what we know about the normal model now can be applied. So I can put an 18, I can add and subtract off the 212, get these values of 11.64, 13.76, 15.88, 20.12, 22.24, and 24.36. Now, what is the probability of packing two systems takes over 20 minutes? This is now how I would write that question in symbols. This curve right here represents P1 plus P2, packing two systems. So 20 minutes falls just shy of 1 standard deviation, and taking over 20 minutes would be to the right of that. Now I'm using knowledge from earlier in the course. How do I find that percent or that probability? Well, the first thing I'm going to do is convert 20 to a z-score by subtracting the mean and dividing by the standard deviation. That's going to be just under 1. In fact, it's 0.94. So this now converts to the probability of z being greater than 0.94. And to get that answer, you can use your table if you know how to use your tables, or you can use normal CDF, second vars, number 2, over 0.94 means 0.94 to infinity, and we get about 0.1736. So the probability of taking more than 20 minutes to pack two systems is about 17%. All right, next, determine the model for the difference in the packing time and the boxing time. Determine the model for the difference in the packing time and the boxing time. So once again, we have to assume times are independent. Since the individual two events are normal, then their difference is normal as well. So it's going to follow a normal model. The mean of the difference between the packing and the boxing time is going to be 3 minutes. And the standard deviation of the difference between the packing and the boxing time is not 1.5 minus 1, but is the square root of 1.5 squared plus 1 squared. Even though we are subtracting the events, the standard deviation is going to be the sum of the variances. And that value turns out to be 1.80. So the difference in the packing times and the model and the boxing times is 3 minutes with a 1.8 standard deviation. And then always just be aware of which way we subtracted. When it just says difference in times, you can subtract either way. I did packing minus boxing. I got 3 minutes. If you'd have done boxing minus packing, you'd have gotten negative 3 minutes, but we would have had the same standard deviation. All right, now this is where the one problem I have students have the most trouble with. What percentage of stereo systems takes longer to pack than to box? Once again, we just found what P minus B should look like. It should follow this normal model. So the difference in the times, packing minus boxing, should follow these values. All right, so this represents packing minus boxing. They want to know what percentage or what probability takes longer to pack than box. So packing is greater than boxing. Now, we do not recommend that you leave it like this, because with P and B on opposite sides of the inequality sign, because our model is for P and B to be on the same side. So using a little bit of algebra here, I'm going to subtract B from both sides of this equation to get P minus B, and that will leave me with greater than 0. And one of the hardest things for you guys, for some of you, is where does this 0 come from? But remember, this model is for the difference in the times. Whenever you want to know longer or more than, or how much more, or how much longer, or how much less, you want to look at the difference in the times. And then it's going to be greater than or less than, depending on the problem, 0. Because if they were equal, if packing was equal to boxing, P minus B would be 0. 0 is about right here. Now, on one side of this curve, packing is greater than boxing. On the other side, packing is less than boxing. And here I get greater than 0. That's to the right of that 0. If we would have had boxing minus packing, like we were doing, I talked about a minute ago, B minus P, we'd still have a 0, except it'd be over here, and we'd be less than, because this time the variables were flipped around. All right, just like we always, when we want to find these values, so we're going to convert this 0 here to a z-score by subtracting the mean and dividing by the standard deviation. I'm getting a z-score of negative 1.66 repeating. I'll round that off. So this will convert to z being greater than negative 1.67. Hopefully you can tell that's going to be more than half, more than 50%. But you can find that answer either in a table, in your normal probability tables, or in your calculator, normal CDF. Greater than means we want to go from this z-score to infinity or to 99. And I'm getting 0.95, or about 95% of the time. It'll take longer to pack than to box. This chapter has a lot of information on it. These problems are really important. I guarantee you they'll be on the AP exam, as well as your discrete ones. Probably more of these than a discrete, but finding the expected value of a discrete random variable is a typical multiple choice question on the AP exam. Please make sure you can read what can go wrong, recap what have we learned, and those AP tips. And what I just said is finding expected values from a probability distribution is a common multiple choice question where you're using this formula, the sum of x sub I times p sub I. That is a very common question on a multiple choice question.